The Jaeger program was born.
Yeah, we're live. Hi, Martino.
We're live?
Yeah,
Hey,
we're
hello.
live. Hi. Welcome to our new episode of the SEED Weekly Live Show. I'm Elaine Wu, head of AI Robotics at SEED. And today I invite a special guest from Hugging Face, Martino, the embedded engineer from the Hugging Face. And
Hello.
we will sit together and talk about their new released humanoid robot project called HopeJR. Welcome, Martino.
Yeah, welcome. Thank you for having me. I landed in Shenzhen about 4 days ago, and it's been wonderful so far. So yeah, thank you.
Wonderful. I believe you're also super tired. Actually,
Yeah.
as you can see in the very beginning. So we have the non-stop, these 3 days, mini hackathon at SEED office. So we literally to have this HopeJR assembled from 0 to 1 in the SEED office. So I think you must have the deeper feelings about the Shenzhen, like how you make this robot from the 0. How do you feel?
Yeah, so it's quite different from the way one develops a robot in Europe or in the West, because you usually iterate on multiple on different parts, and you have to wait for the parts to arrive. So like that can take maybe a week. Then you realize that your prototype wasn't working that well, so then you order more parts. You wait another week, and usually like what you thought was going to take maybe 3 days takes 3 weeks. Now, what shocked me is that in Shenzhen we order stuff and it came in a matter of hours. So one such example is magnets. We ordered diametric magnets, which is a specific type of magnet that is not magnetized along the poles, but it actually has north and south pole on both faces of the cylindrical magnet. And yeah, we ordered those, and they came in like 2 days. And that's something that takes weeks to order in Europe. So that definitely shocked me.
Actually, it's 2 hours delivered.
Sorry, hours, not days. Because it's so unreal, like that could happen. So yeah, definitely pleasantly surprised by that.
Yeah. And so actually, literally in Shenzhen, you can achieve, make, and build almost anything in Shenzhen. Yeah, I think this will be the fastest city in the world if you want to build up something. Yeah, so as Martino mentioned, so we got everything besides the magnets delivered. So we want to show you what happens in this crazy 3 days. So first, in this picture, we get everything delivered, and that including fishing line, magnets, springs, screw, servo, sensors, 3D printing parts, etc. The kind of the difficult parts of this is we received the BOM first, but then we realized that there is something need to change, and then we quickly buy the new ones. But it's good. Yeah, we get everything. And then we started our 0 to 1 fabrication. It's pretty smooth. So we start get the PCBA in the office, and then
I
started.
was shocked about how the PCBs were assembled in the office here at the studio.
Yeah,
It's
exactly.
something I haven't seen before.
Yeah,
in the really complicated PCBs to assemble, but the guys here did a great job.
Yeah, thank you. We're like a huge makerspace at Seed office. And then we started the mechanical, and thanks to Ifan, our mechanical engineer, and manufacturing, runs optimization, and then the testing, assembling in the meanwhile, and also the validation for the different parts. And then finally, why can we make it in this very short time? I think besides the delivery, we also, because it's all happened in the Seed office, so we have software team, electronic team, and also embedded team, and also the mechanical team to support very in time. So we can also get the real-time validation.
Yeah.
Yeah. So although we're in that small office, but we made it.
Yeah.
Yeah.
We didn't have a lot of space, really. That was the main issue.
Yeah. So before we dive into our main role today of the Hope Junior, I want to have you take a look. There are a lot of new robots Hugging Face released this year. Very exciting. They released 4 robots. So first is SO arm 101 is the one pair of the robot arm, and
the flagship of the LeRobot, we would say.
Yeah, the LeRobot, the start one. The starter one, and then you can directly get them at the store right now, and we have a bunch of the tutorials then. So in very soon we're gonna release the Kiwi. So the Kiwi is the same SO arm, but it comes with the wheel, the chassis.
It's a mobile version, basically.
Yeah, is it the slightly the different version?
I would say like the Omni wheels that you see, it's quite peculiar the way it moves. The wheels basically have wheels on them, so you get motion along the perpendicular to the axis of the wheel, but also like parallel. So and if you put 3 of those at 120 degrees from each other, then you can move basically in any direction and rotate as well, which is quite interesting. It's a cool robot. Shout out to Pepine, who sort of integrated the S100 with this Omni wheels.
Yeah, and also it supports both Pi, Raspberry Pi, and also the Orin Nano as the main controller. Yeah, and then you just released the Hope Junior. Hope Junior actually is a open source DIY humanoid robots with dexterous hands. But today we're only introduced the arm and also the hands parts. And also together with the fingers and also exoskeleton, right? Yeah, and so Martino, all the robots we mentioned actually
Wait, no, they're saying that it's loading. The live is loading for some people.
Loading what?
Broken live.
What?
Some of the comments are saying that the live is broken. Is the live working fine? Or is it just? It's back. Okay, it's back.
It's back?
Okay, yeah.
Okay.
Ah, cool.
It's
Thank
work?
you.
Okay, we continue. So all the robots we mentioned, Junior, the SO arm, the Kiwi, and Richie Mini, so they will also support the robot framework, right? So we in January this year, we had another live stream talking about SO arm and also the robot. So I want to quickly introduce again about the robot framework. It is an end-to-end robot learning framework, offering all the robot control interfaces, data sets, recording, editing, visualization, pre-trained models, and also policies for imitation learning, and also refers
library, which is
all in the single library.
The only library.
Hence, in total, it includes 23 degrees of freedom, and there are 16 in the hand and 7 across the arm, as is highly articulated movement. And also it teleoperated with the LeRobot, right? And then the power and the policy is also trained by the robot. So
the entire thing is just handled in by the LeRobot library, from the teleoperators to the robots to the training policies. It's all done in LeRobot. Yeah.
So Martino, can you closely, we mentioned, so in total there are 4 parts. So arms, hand, fingers, and also exoskeleton. So can you introduce each part, what are they and how it works?
Yeah, so essentially this is a 7-degree of freedom arm, if you exclude the hand, which has 16 degrees of freedom. And we use VTEC motors to actuate the arm. So just like with the S100, this is the same technology basically. And yeah, so we get really, very, very big, we get very good resolution from the motors, and it allows for very smooth and precise motion. So yeah, so about the arm is the same degrees of freedom as a human arm, and regarding the hand is a tendon-based hand. So if you can just show the audience. Whoop. I guess maybe just turn around like this. Yeah. Okay. So the idea with this is there's smaller motors in the hand, and these are connected by wires to the fingers, and these wires allow the fingers to move inside, basically, towards the palm, and they're retracted then by some springs. So the hand has full dexterity. Speaking of oh yeah, I mean, if we can still if you don't mind, you can also turn this up. There you go. Okay, yeah. So the hand has full dexterity, and by which I mean is for every degree of freedom of a human hand, that gets mapped onto the physical robot. So if you take a look at the ring finger, for example, I can move side to side, I can move it up and down, and I can also flex the finger. So that gives me 16 degrees of freedom total for the hand. And okay, thank you. Yeah, so as I mentioned, as Elaine mentioned, this is integrated into the LeRobot library, and that means that it's possible to not only teleoperate this, but also to train policies that run on the arm itself. So you can train it on a variety of tasks, like grasping, for example. Or some more sophisticated stuff, like pen manipulation. Sorry, like pen manipulation or just dexterous manipulation in general. And yeah, and then as Eddie mentioned, there's the second part of this, which is the teleoperator. So this is the homunculus exoskeleton with the homunculus glove, and it tracks every degree of freedom of a human arm and hand, essentially. Which it's accomplished by using Hall effect sensors and magnets. Basically, this means that compared to traditional encoders, this will never break, essentially. Like the linkage will break before the Hall effect sensor and the magnets do, because they're not touching, essentially. And I would say that's about it. There's some custom PCBs that have been developed for this teleoperator, and they basically boost the signal that's coming from the Hall effect sensors, which are chosen because they're particularly cheap. And yeah, so we're trying to keep the cost of this whole thing down as much as possible. So we take this really cheap equipment, and then we boost it basically in order to make it more, in order to make it make it worth our buck, if that makes sense.
Yeah, I believe this will be the world's first the DIY humanoid robot arm and dexter hands for the humanoid and embodied AI. Yeah. Martino, I want to know there are so many parts. So for the
There's
assemble,
a lot of parts.
Yeah, a lot. So I want to know what is your suggestion, or what is the most the difficult parts for the assembly, and then the developers should be aware of.
For sure, the most difficult part of the assembly is the fingers, just because of how complicated they are. I would say, when you say that that the hand has 16 degrees of freedom, it also means that it is made out of 16 different joints. Actually, more than that, because the tip of the fingers is under-actuated, but it actually moves, kind of like our fingers. So in a way, it's possible to move this joint, but it's really difficult to move this joint in isolation. But you do need them both in order to grasp. So there's a lot of moving parts in the hand, and those are very difficult to coordinate essentially. The building process is difficult to coordinate. So I would say that is the most difficult part of the assembly for sure. And yeah.
And also for the 3D printing parts, so will you maybe consider about using the aluminum?
It's definitely possible, although the design would need to change significantly because some of the parts of some of the parts of the exoskeleton are very flat, so they would fit an aluminum build very well.
Yeah.
But for the arm, some parts are a bit bulky, so they would need to be redesigned for sure. But it's an interesting idea, definitely.
Yeah. Okay. So after we see this, if we want to get started right now, where we start?
Yeah.
Is start from the assemble, calibration is everything in the Hugging Face documentation, correct? This one.
Okay. Yeah, sure. So
Can you quickly go over this documentation?
yeah. So the first thing obviously is install the robot, and once you've done that, you order yourself all the parts basically that are required. There's really the BOM in total is about 500 euros, and that covers the cost of the VTEC motors, the cost of screws, wires, and whole sensors and all everything you need basically. So once you order your parts, you can then start assembling the Hope Junior. The first thing you need to do is configure the motors because those need to be calibrated for this specific application. Specifically, the ranges need to be tuned, the IDs need to be set, and yeah, that's the first part essentially. We're going to be releasing a build tutorial soon, which should help you. Should help you with the assembly. And I believe Sistu will release also assembled arms.
Sure. So we will resemble that and record all the steps and then publish. Yeah.
Yeah. So. Okay, yeah, and I would say the first part to start with, because this is actually modular, so you can actually build the hand in isolation from the arm. It's sort of involved, so I will start with the hand first, and yeah, so you get wire essentially, and you connect all the motors to the to the fingers, basically to the spools. Yeah, again, we're not going to go into detail on how the build process works. You just follow the tutorial once it comes out, and that should be enough. The second step is the calibration. So essentially, you wanna make sure that you wanna normalize the values of both teleoperator and robot. And what I mean by that is these motors actually can perform multiple revolutions. Yes, thank you. They can actually perform multiple revolutions, but we only care about a specific subset of range for each motor. So that means that we want to map 0 and 1 onto that min and max range. And we do that for the motors, and we do that also for the teleoperator. So we want to find out what are the ranges of the limbs of the human operator. And once you've done that, mapping is relatively trivial because these two devices have been developed in cohorts. So every joint of this teleoperator will map onto a joint in the Hope Junior, which is a situation that is quite unique, especially for grippers. One thing that happens with grippers often is that you want to be able to teleoperate them, but they either don't resemble a human hand, so you need to make a specific controller for them, or they have a different amount of degrees of freedom. But since these have been developed simultaneously, we don't run into such issues. So it's just a direct one-to-one mapping, and that's all handled by the LeRobot teleoperator class. And I would say, that is it. Once you can teleoperate, you can also record data. You can upload it to Hugging Face, and there's a very nice GUI actually that allows you to sort of watch your data sets, and it's really cool because you can see you basically get a live plot for all the degrees of freedom, and you can also get like a camera feed if you wanna have that, and yeah, so that's how you record the data set on this. Once you have a data set, then you can train on the policies that we also have available at LeRobot. So that's that's about it.
I want to know now the data sets is all coming from the teleoperation. So will in the future you also support the simulation?
Yes, for sure, for sure. Simulation is very useful, especially because of how fast it is. You can simulate multiple robots at the same time, and that significantly speeds up training. There are some issues at the moment for the simulation of HopeJR because there's so many moving parts, and they're very difficult to simulate simultaneously. Yeah. For example, like strings, that are not something that's easily
Right.
that's easily simulable. I guess I don't know what the word is. Yeah. So then once you've done yeah. So like once we manage to form a simulation for the robots, then we can add the simulator class.
Do you mean the force and also the weight and also these small components will be
That's not
further simulated?
That's not that much of a big of a problem. You can simulate torques easily. It's just like the fact that like springs, friction. That's all. That's all difficult to simulate.
I see.
Yeah.
Great. So for the LeRobot, it includes many policies, like ACT and also diffusion policy.
Yep.
Yeah. So and etc. So what is your most recommend? So if people want to train the policy right now.
Definitely the most straightforward one is ACT. There's also, with the most advanced one being reinforcement learning, HIL SIR, so human in the loop SIR is definitely the most difficult one to get to run. But it's been done by our team did an amazing work on it. And if you want to, sort of test your skills, it's really interesting because you watch to see the robot learn in real time. So that's the one. That's one I use most often, and that's my favorite personally. But if you're just getting started, I would focus on ACT. So it's a simple imitation policy with a variational autoencoder that guides the actions. That's one I would suggest. We also have diffusion policies and policies coming from the community. So definitely feel free to explore and figure out which one. Just ask around also, basically.
Yeah, sure. So how many episodes for the training and how long time?
For imitation learning, it doesn't really take that long. You can also train on Mac, and that's really straightforward. And it takes about I would say about 10 hours, depending on the task. So you can really get away with having not that many episodes. Just get it. For example, one policy I trained is for the rock paper scissors, so just on the hand, and that was done with I think maybe 100 episodes, and it was trained in under 10 hours. So then you have your own policy, and just as an example, the way that worked was you have a video feed, and the robot was trained to always beat you at rock paper scissors, basically. So if the camera if you would show the paper to the camera, then the robot would do rock, and scissors with the paper, whatever. You get what I mean.
That's cool. Yeah.
Yeah. I think we need to stop it. Oh shit! Yeah, no, stop it. We've been teleoperating for a long time. We've been rehearsing, so.
Yeah.
Yeah.
Okay. So, Martino, I want to ask. So this is the first DIY open source humanoid robot arm and with a detector hands. So I want to know why Hugging Face do this open source.
Yeah.
Yeah.
The idea with open source, especially in the design phase of a product, I would say, is to to gather feedback on the
community.
Yeah, from the community on the products that are being developed. So I would say that's the main focus. So just having making sure that everybody can contribute, and they can sort of fine tune the robot to their liking. So Hugging Face is the perfect hub for that. They were already known for open sourcing a lot of software, namely transformers library, diffusers, and all that. But now they've moved onto robotics because that's the next big leap in the environment.
Yeah.
So again, as you said, we support multiple open source robots, and And yeah, and you can find them all at the Hugging Face / LeRobot.
Yeah, sure, I do agree. So that is how charming of the open source. I think in a way it's the open source setting up a higher threshold of this technology standard. And in another way is open source is also pushing us to make this better and also moving much forward.
Yeah.
Yeah.
Should we answer something
Yeah, we should
the
answer
question?
some questions.
So,
So
like,
first, Jason C, can we buy the hardware soon? Yeah, we are working
Very
on
soon,
we,
yeah.
we're very soon. We are working on that and still optimize on that. So once it's available, we will let people know when it will be in stock as seed, including all the parts and tutorials. Yeah, and robot, how many joints does each fingers? And
yeah, so Robert has you have a lot of good questions,
Yeah,
Robert. Sorry
yeah.
for waiting for so long.
And why did you choose
so-
that number?
Yeah, so I mean, so two things. So the if you read for the hand, if you read anatomy papers and sort of if you study how it works, there's many more muscles than 16, but the number of joints in terms of bones that are able to be actuated by the human hand is actually three per finger. So we have the MCP, PIP, and DIP joints for each finger, and the thumb is an extra degree of freedom, basically. So that in total makes 16. So that's why we chose the number. And I mean, the arm, if you exclude the movement of the shoulder, also has 7 degrees of freedom for similar reasons. But the fingers are way more complicated than that, actually. There's like there's like tendons that's like above the knuckle, and it's kind of hold it into place. But as a simplification, I think 16 is a good value. Then I think the more important question you was asking, like, what are the safety procedures that you have in place? So the motors actually are capped in terms of torque. So we limit the amount of torque that they can output. And if the motion that we are planning from the teleoperator demands more torque than that, then the torque will drop to a safety level. So that ensures that the arm cannot hurt anything, including itself and its surroundings. Of course,
heavy?
accidents can still happen. It could knock down like your laptop or like a glass of water or something. But that's to be expected, I think.
Yeah. And how heavy is the arm?
The arm is about, I think, 2 kilos.
2 kilos.
Yeah.
Not very heavy. And you say, are there any sensors built in?
Yes.
Robot.
Unfortunately,
Always have the good questions.
You came a little late. Yes, we can definitely do the gesture, but the arm is being shut down now because it was overheating. So we can maybe sort of manually do it. I don't know. He doesn't know what the gesture is. It's okay.
We teleoperate many times. It stopped right now. It stopped. It worked again.
No, I did it.
Okay.
No,
Mechanically.
all right. That's good enough.
Which control architecture do you use?
It's just position-based control for now. We're planning to move on torque-based control, and that's going to be the next step. Actually, we're planning to achieve that using series elastic actuators on both the arm and on the exoskeletons. So yeah.
Okay, Robert, I really look forward to your feedback when you
going to
really
submit it
receive
to the-
that and play with that. And can we buy there any sensors? What type of sensors for grasping? Pressure or?
Right now we only sense to detect grasp we use the torque coming from the motors. So it's not very reliable. You get about 12 values of pressure from each motor, but then you can use them to detect whether like grasping has been performed. Our plan is to use proper touch sensors. We were looking into magnetic touch sensors such as AnySkin, which basically use the magnetic particles and Hall sensors in order to detect pressure. Yeah.
Are the motors the same as the SO arm, FITAC, ST3250?
So in the arm, the
same.
motors are exactly the same as the
Okay.
FITAC, except as the S100, except for the shoulder. The shoulder motor is much beefier because it needs to hold the torque from the entire arm. So we need to use an SM8512.
Yeah, sure. And also the servers is also available as seed. Okay. Yeah, I want to know what is the some exciting applications or fun applications on your mind?
Let's see. I would say the one. I mean, personally, I would like it to play games. Cooking also is one that I would really like to automate because I hate cooking. Yeah, but we're definitely far away from doing something like surgery or like some more some applications that require like a more precise control. And yeah, so for me, those are the two ones that I'm looking forward to.
Cooking and cleaning something.
I guess, yeah.
Yeah.
We've already done folding clothes, so just housekeeping stuff for now. Yeah, just basic applications basically for now. But the idea is like this should be a good seed for people to then try and experiment and see what can work and what doesn't. It's meant to be like a general purpose device, I would say.
And Frey asked, can this robot do the magic?
No, we already answered. We already answered it.
Okay.
We definitely already answered it.
Can I use it to get massage?
Probably, yeah.
Probably.
I have not tried that, but it should probably work. Yep.
Okay, cool. So, what is the future plan for Hope Junior?
Yeah, as I mentioned, the next thing we will do is add force feedback to Hope Junior, and once we open source it, we get a feedback from the community, and we see where it goes from there. Yeah, so I think that summarizes decently well, I would say. And of course, I mean, this is gonna have to be integrated with the humanoid. Using just having torso, legs, and all that, 2 arms, and seeing what that can do, basically.
Yeah, sure. And I think we have other rounds of the optimization. So just stay tuned with Seed, with our wiki page, social media. And so we will keep you updated when it's available and when we're more ready for having that. And also there some it's a loan said they will try it in Genesis simulator. That would be cool. And I also look forward. To integrate the NVIDIA GUT N1.5, the world's foundation model, including the datasets of the raw data simulated and also video. I also look forward to that because that is already achieved in the ISO ARM. Yeah. So that would be very cool.
Just one quick answer. So Susha says, why not use potentiometers? Yeah. Well, we don't use potentiometers because Hall sensors are clearly better in that they don't break over time, and magnets are cool also. That's the answer.
Okay, cool. I don't think we have more questions. Yeah, this will be cool. Yeah. So I hope one day you will come back to Shenzhen again.
Of course.
Yeah.
Building in Shenzhen is incredible, and maybe for the next step of Junior, if I prototype something, I'll come back here and do that because we'll be way faster, for sure.
Yeah, and also November we have the Maker Fair, the very big maker show and exhibition. We're hosting that in Shenzhen, so welcome all makers and robot companies and come to us and see how fast you can build almost anything in Shenzhen. Yeah. Okay. I think it's our live today. Thank you, Martino.
Thank you.
Yeah.
Thank you to you.
Thank you. Stay tuned with us.